I will present the scanless fluorescence lifetime microscopy using a dual-cone optical bead. Go to background. Fluorescence lifetime imaging microscopy, or FLIM, is an interesting imaging tool for the life science and biology. When a sample is excited by pulse light, the fluorescence shows a decay curve like here. This decay curve is given by this equation where the tau is a fluorescence lifetime. So in this way, the time domain FLIM will measure a temporal response of fluorescence to impulse excitation. Fluorescence lifetime is independent of concentration of fluorescence molecule, photobleaching, and excitation or detection efficiency. Also, it is sensitive to change in microenvironment around the fluorescence molecule, such as the temperature or pH. Furthermore, it is possible to distinguish even the fluorescence molecule having the same fluorescence color based on the fluorescence lifetime, like here. In this way, the FLIM has a higher quantitativeness than the usual fluorescence microscopy. Time domain FLIM can be classified in two types. One type is the laser scanning FLIM by time-correlated single photon counting, like here, using this setup. So it has a high sensitivity around the photon counting level and high time resolution around a few tens picosecond. However, the imaging rate is limited to several FPS due to the mechanical scanning of focal spot with a Galvan mirror. Another type of time domain FLIM is a full field FLIM by time resolved or time-gated camera, like here. The imaging rate is relatively high due to the full field imaging with the camera. However, the time resolution is limited to a few nanoseconds due to the gate time of camera. In this way, the simultaneous achievement of high imaging rate and high time resolution is still difficult in time domain FLIM. Another type of FLIM is a phase modulation, or PM FLIM, which is a frequency domain FLIM measuring a temporal response of fluorescent to sinusoidal excitation, like here. A sample is excited by a modulated excitation light at the modulation frequency of F. The resulting fluorescence is also modulated at the same frequency of F in synchronization with the excitation light, like here. Here's a phase of the modulated fluorescence is delayed by phi from the excitation light, depending on the fluorescence lifetime. Since fluorescence lifetime and phi is given by this equation, the tau can be determined by measuring the phi at the known B. So such a PM FLIM has a real-time point measurement, high precision measurement, no requirement for fast detection system. However, it still requires a mechanical scanning of focal spot for 2D image. So this PM FLIM can be especially multiplexed by using a 2D array of excitation spot having a different modulation frequency. The resulting image acquisition time will be largely reduced. To this end, it is a key that the 2D array of excitation spots, or PI, correspond to the different modulation frequency of excitation, light, BI, to have a one-to-one correspondence between them. So if such a 2D array of excitation spot is used for the FLIM is specially multiplex by using a different modulation frequency. The resulting 2D array of fluorescent spots, so Pi, correspond to the fluorescent modulation frequency Bi in the same manner as excitation light. However, there are some difference of amplitude and phase between fluorescence and excitation, depending on the fluorescence intensity and fluorescence lifetime. We next consider to detect a 2D array of excitation spot collectively by a point photodetector. Also, we consider to detect the 2D array of fluorescent spot collectively by another photodetector. So this slide shows the frequency domain description of detected RF electric signal. Upper shows the RF spectrum of amplitude and phase for excitation RF modulation signal and fluorescence one. So again, so that each mode, so based on from the one-to-one correspondence between the excitation spot Pi and modulation frequency Pi, each mode pair of amplitude and phase at the modulation frequency Pi correspond to the 2D array of excitation spot, fluorescence 2. So amplitude ratio or phase difference between the fluorescence and the excitation light at each modulation frequency Bi gives the fluorescence intensity and fluorescence lifetime at each spot Pi. But how so we can generate the 2D array of excitation spot having a different modulation frequency? The answer is given by a pair of optical frequency comb, namely dual optical comb or dual comb. So the optical comb is composed of a series of frequency spikes regularly separated by a constant frequency. So here we first prepare OFC1 with a frequency interval of FREP1 as the first comb. So when the OFC1 is incident onto the 2D spectral disperser, 2D spectral graph of OFC mode is generated at the optical Fourier plane via the wavelength to space conversion. So this is corresponding to the 2D array of excitation spot without the amplitude modulation. So here the 2D spectral disperser is composed of Viper and grating. We next prepare another optical comb, slightly different frequency from FREP1 as a second OFC, second comb, namely OFC2 with a frequency spacing of FREP2. Each mode of FREP2 is said to be close to that of OFC1, like here. Then the OFC1 and OFC2 are specially overlapped and fed into the 2D spectral disperser. This results in generation of 2D array of focal spot for OFC1 and OFC2 indicated by solid line circle and dashed line circle. In the frequency domain, the two adjacent modes of OFC1 and OFC2 generates an optical bit signal between them in RF region, highlighted by purple color. So this is a dual optical comb RF bit, like here. So it is a frequency multiplex signal separated by delta FREP, where the delta FREP is a frequency difference between FREP1 and FREP2. So in the space domain at the focal point, there are two adjacent modes of OFC1 and OFC2. Many pair of two adjacent modes in OFC1, OFC2 make a focal spot to the array of focal spot at the almost same position. So the overlap area between the overlap area of each spot. So highlighted by a purple color generates a dual optical RF bit. So in this way, the one-to-one correspondence is established between the overlap spot area and the dual optical RF bit. In other words, RF multiplexing of excitation light is achieved in frequency domain and image domain. So this can be used for 2D array of excitation spot having a different modulation frequency, so enabling the spatially multiplex PM3. Okay, so next shows the experimental setup and sample. Here we use a pair of albumin fiber comb at the 1.5 micrometers, so OFC1 and OFC2. Specification of them are indicated here, and frequency delta F-rep between F-rep1 and F-rep2 was set to be 978 Hz. So this is a maximum imaging rate of this the present spatially multiplex PM3. And the metal light from OFC1 and OFC2 are converted into the THG light around 0.52 micrometer. So this shows the optical spectra of the resulting green OFC for OFC1 and OFC2. We having optical power of 10 milliwatt. And then, so these two green OFC are spatially overlapped and then fed into a combination of Viper, grating, and relay lens. This result in generating a 2D array of excitation spot with a different modulation frequency on the sample at the sample surface. Here we use a sample composed of test target and the chamber, including containing the fluorescence solution. So when the excitation light is incident into the sample, a 2D image of test target appeared due to the fluorescence. So this fluorescence image is detected by a photomultiplier tube, so PMT2. Portion of the excitation light is also measured by another photomultiplier tube, so PMT1. The detected RF electric signal from the PMT1 and the PMT2 were acquired with the first digitizer. We first demonstrate the scanless imaging of fluorescence intensity and lifetime. Here we use a rhodamine-6 aqueous solution having the emission wavelength region of 543 to 617 nanometer and fluorescence lifetime of 4.08 nanosecond. Left shows the temporal waveform of fluorescence RF signal. Then the Fourier transform of this temporal waveform gives the amplitude spectrum and the phase spectrum of fluorescence RF signal. So the both spectra are containing the 44,400 mode, respectively. So that this value is corresponding to the total number of image pixels in reconstructed image. Also, the spectral envelope reflects image information of the fluorescence intensity and fluorescence lifetime. And then, so we calculated the amplitude ratio spectrum of fluorescence to excitation light. And then, so based on the one-to-one correspondence between the PI and BI, the fluorescence intensity image is reconstructed like here. Also, the fluorescence phase delay image is reconstructed from the phase difference spectrum between the fluorescence and excitation light based on the one-to-one correspondence. Finally, this fluorescence phase delay image is converted into the fluorescence lifetime image based on this equation. In this way, the Three image clearly shows test chart pattern like here. However, the image contrast mechanism are different among them. So the fluorescence intensity, fluorescence phase delay, and fluorescence lifetime. The lifetime value of this image is in good agreement with the literature value of this sample. We also investigate the dependence of image SNR on the number of accumulated image. Left shows a comparison of the accumulated image with respect to the 100, 1,000, 10,000, and 100,000 images, which are corresponding to the data acquisition time of 100 millisecond, 1 second, 10 second, and 100 second. So the image contrast is increased by increasing the number of accumulated image. Right shows the image SNR with respect to the number of signal accumulation or corresponding data acquisition time. Image SNR linearly increase depending on the square root of the number of signal accumulation. So this indicates the short noise limit measurement was achieved in this demonstration. Finally, to investigate the quantitativeness of fluorescence lifetime measurement, we perform the film imaging of 4 different samples having the different lifetime. So 4.1 nanosecond for sample A, 1.8 nanosecond for sample B, 2.4 nanosecond for sample C, and 3.0 nanosecond for sample D. Right shows the relation of fluorescence lifetime between literature value and measured value, indicated by red plot. And then we perform the curve fitting analysis with a linear function, like here. So a good relationship was confirmed for this sample. When the accuracy of fluorescence lifetime measurement is defined as the root mean square error between the experimental plot and the linear approximation curve, the accuracy of fluorescence lifetime was achieved to 0.07 nanosecond. Finally, we summarize the present talk using this slide. Thank you for your kind attention.